We'll proceed with John Bosch telling us about software engineering for AI.
Thank you very much, sir. Appreciate it. Good morning, everyone. How are you? Arr! A little bit more energy in the room wouldn't hurt anyone, I think. So, how are you today? Excellent. It's good. Happy to hear that. My friends, we're going to talk a little bit about software engineering for AI. I'm one of those solution-oriented people, but I'm going to talk about problems today. How's that? Huh? Is that funny? I don't know. I don't think it's very funny. But here is how I'm going to frame the whole situation. I'm going to show a scenario for you that I've seen play out dozens of times with various companies that we work with. Meet Jonas. Yeah, a fine Swedish gentleman, right? Jonas has a problem. But he thinks, I have a solution to this problem because he has an idea. There is this thing called AI. Let's go and use AI to solve the problem that we have. And how do I do that? Well, you know, I get some data from the data warehouse and I put it in a nice and cute data set. And then I grab a number of machine learning and deep learning models. And then I go and train it. I go and train the model using the data that I have available. And you know what? We're successful. The prototype works fabulously. Yeah, we have great accuracy, very low error rates. Beautiful. So everyone is standing there on their chair shouting, yo, let's go and let's deploy this whole thing. So we're going to put this thing in operation in practice. And you know what happens? It fails. And why does it fail? What happens? Why is it so hard to take things from production, from piloting and prototyping to actual real industrial production quality deployment? And I haven't really seen a big pattern there, but it's either data pipelines that fall over, it is internal cultural conflicts, it is organizational issues, it is a variety of different factors that is causing this. And that's what I wanted to spend a little bit of time with you on in the coming 30 minutes. So, and this is for, I'm going to kick some of the people in the shins here because not everyone likes this analogy, but I mean, what is the difference between these two items of construction? A doghouse and a number of skyscrapers, yeah? So it's, I think, pretty obvious. A doghouse is small scale, very few people are involved, it's mostly concerned with pilots and prototypes. There is no little societal value for doing this, and there's no risk. If you make a mistake building a doghouse, your dog may get wet when it rains, but you know, no, it's okay, right? It's a dog. Okay, sorry, that was the wrong statement in this audience, I suppose. I'm from the Netherlands originally. We care less about dogs, I guess, than people here in Sweden. I'm not sure if that was a politically correct statement. Okay. You know, in American English, there's a saying, when you dug yourself into a hole, stop digging. So that's exactly what I'm going to do right now. What is the thing with the skyscrapers? Well, skyscrapers are large scale. They involve hundreds or thousands of people. It is industrial critical deployment. It has high societal value, and it also has high risk. And here's the interesting thing, where I'm going to kick some of you in the chins. Most academic research is actually concerned with small-scale efforts. Yeah, basically we're talking about studying the applicability of technology. Could I apply this technology to this situation? But and this is all fine and useful, but it needs to be complemented with something else, and that's what we call engineering research. Engineering research is concerned with studying whether a technology is actually beneficial and whether it's actually scalable in an empirical real-world context. Yeah, interestingly enough, we found several cases where people went out and started to employ all kinds of great deep learning solutions, and then it turns out that a basic, simple statistical approach going back 100+ years actually worked better than a deep learning algorithm. Yeah, so even though the feasibility was there, the benefit wasn't necessarily there, and things do not necessarily scale. And I think that it's important to understand you can not have the one without the other. Of course, we need the traditional scientific-oriented research where we look into the applicability of technologies, but we also need the engineering research in order to be able that we can actually grow and scale and deploy this technology in a real-world context and understand what the challenges are that come with that. Because until we can actually take all the great output that we get out of the WASP program and deploy it in society, until we can actually make that impact, it has no impact. There is no impact on society. It's just a number of smart people talking about fun things. Yeah, and I'm not the only one that thinks this. This is a few quotes from KPMG. The AI deployment of integrated and scalable solutions across business requires more than data scientists. Or another one out of the same article, one of the biggest problems facing business is getting AI from pilot phase to scalable deployment. This is a real problem that is becoming increasingly recognized out in industry. So another interesting perspective on all this is an analysis of what are the 5 most important jobs in AI in 2019. And it turns out that it's an AI architect, it's an AI product manager, a data scientist, a software engineer, and an AI ethicist going to the program that was just being presented here, right? But the interesting thing is that 3 of the 5 jobs that are considered to be the most important jobs in AI are actually software engineering positions. Architects, product managers, and software engineers are obviously software engineering roles. Yeah? And I think it's important to reinforce that. So what are my 3 key takeaways? The first is, we are in the midst, and everyone in this room understands this, in a fundamental shift of society, driven by digitalization. We define digitalization as having 3 elements. It is software, it is data, and it is artificial intelligence. You need all those 3 things. You cannot do these things in isolation. And to be honest, even though some people feel like, oh, we've already come so far in this journey, I believe that we've only barely started to scratch the surface of the remaking of society that is being created by the forces of digitalization. Second, if we want to take machine learning and deep learning solutions and actually productify them and put them in large-scale deployments out in industry, then what you actually see is that this is a major engineering challenge, something that I think as a community, especially as a research community, we have been significantly underestimating, and we need to spend more time on that. So my claim, and this is the 3rd takeaway, is that research on AI needs to be balanced with research on software engineering for AI in order to support production quality and scalable solutions. Otherwise, you know, we can do great things in the lab, but it will never see the light of day out in the real world. And I think that that's one of the key things. And some people are taking pictures, so I'll wait for a second. How's that, right? So the research that we do in this, we have a PhD student or a few PhD students from WASP, but most of this research we do in the context of Software Center. Software Center is a collaboration between now 13 companies. The latest company to join was Wärtsilä, the Finnish company building ship engines and power plants. But we have a wide variety of companies, mostly European ones, where within the context of Software Center, we aim to significantly improve the digitalization capability of the European software-intensive systems industry. And as I say digitalization, remember that I mean software, data, and artificial intelligence. Now, what is important is that we do not view AI in isolation. We've defined something in a project that Ivica and Elena are part of as well, something that we've called the Holistic DevOps Framework, or the HolyDev Framework, where we basically say is that modern software development in companies will consist of 3 different types of development. We will have the traditional requirements-driven development. That's when you have features that are just specified using traditional requirements. Typically, these are features from regulators, competitor parity features, so we know that our competitors actually have these features, so we need to have them as well. Or commodity features, features that are not differentiating. They do not cause customers to pick our product over another competitor's product, but you still need to have them, because otherwise, if you don't have them, you cannot even sell your product. The second type of development that we're seeing is what we call outcome or data-driven or experiment-driven development. This is when you have a certain value function or a value hypothesis, something that you want to improve, and then you do things like A/B testing, which happens a lot in websites and in online companies, but is now also starting to be used in embedded systems. So I do A/B testing, and rather than giving teams requirements, I tell them, you have to improve this KPI of the system, of the product that we have in operation. In e-commerce, this may, for instance, be conversion, but you can't damage any of the other requirements. And however you want to do that is entirely up to you. You can run different types of A/B experiments, you can redesign your system, you can do ethnographic studies, but you have to move the needle on these outcome metrics. And this is typically where we look for features, where we are looking for ways in which customers can get the daily behavior or the daily value out of the system. And then finally, we have what we call AI-driven development, which I think many of you understand. I have a large data set available, I have machine learning or deep learning algorithms available. The data set is of course labeled. I can train the deep learning model or the machine learning model, and what I then get is basically AI components that can be deployed in systems. What is important to realize is that all three types of development are being deployed in one and the same system. There is a system in operation, and that system will have components that are developed traditionally or that are developed using AI techniques. So every one of the blue components can be developed using this approach or using this approach, and then we have AI components that are developed using this approach, but all of these components coexist in one system. They are all subject to continuous deployment. One of the other things that many AI researchers, I think, are missing is if we look at how companies like Microsoft, that we have some collaboration with, work with machine learning and deep learning, the machine learning and deep learning components are retrained every couple of days or every couple of weeks and then redeployed. So there is continuous deployment of all components in the system. And not only that, I also constantly monitor and verify how each of the components is performing out in the field and how the system as a whole is performing in the field, so that I can actually see if things are getting better or worse. And I think it's important to understand this. There is another point to reinforce why we believe, or I believe, that software engineering is so important in an AI context. This is a paper by authors from Google where they basically show the architecture of a deep learning or machine learning model deployment. And if you look carefully, you can see that the little black box in the middle is the machine learning code. Yeah, that's the thing that we have been spending so much time on. But if you look at all the other boxes around it, these are all the things that need to be in place as well in order to make this little black box do its magic. And if you don't have all the boxes around this, nothing works. You can create a beautiful prototype, but you can't actually create a production quality deployment of your machine learning. And this is what we see. What we see is that I love stairways and evolution models, but what we see is that companies move through what we believe is 5 stages of development when they talk about artificial intelligence, machine learning, and deep learning. The first is I work with experimentation and prototyping. This is what happens in the lab. I'm trying to figure out if this technology actually has anything of value available to me. Once I get well-working prototypes, the first step after that is often what we call non-critical deployment of machine learning and deep learning models. That's when you add these things to your product, but if they don't work, you know, they are non-critical, so they will not actually damage the product or the relationship to the customer or whatever. They're more of an add-on functionality than an integral and critical part of the functionality of the system. After that, you move to what we call critical deployment. Then the machine learning or deep learning model actually is a critical part of your product functionality. So you need to have it, it needs to work, because if the machine learning or deep learning model does not perform as expected, the whole product or the whole system will actually start to fall apart. The step after that is cascading machine learning and deep learning models. That's what we see in companies that are a bit more advanced. But there, one machine learning or deep learning model, the output of that model is then used as the input for the next model, and I can have multiple cascading models building on top of each other. And then the final stage is what we call autonomous machine learning and deep learning components, where machine learning systems are built in such a way that they are constantly retraining themselves, redeploying themselves, constantly monitoring themselves, and they become much more autonomous and require much less human involvement. Now, as long as you are in the experimentation and prototyping stage, software engineering is not important for you. But if you want to get to the stage what we at Peltarion call operational AI, then you need to, once you hit these stages, you need to have and get much more serious about software engineering for machine learning and deep learning. So that's one of the things that I'm trying to get across. The final takeaway, before I go and talk a little bit about some of the studies that we've done in this space, we've done 3 studies that I briefly want to share with you. We've done a lot more, but these are the 3 that I picked. If we look at a typical machine learning or deep learning context, there are 4 activities that happen in a sequence. The first is you need to assemble the data set. Once I have a data set, I can create a model. Once I have created a model, I can go and train and evaluate. And then after I've trained and evaluated the model and I feel that it's sufficiently mature so I can actually deploy it, I go to deployment. And the interesting thing is that there are 2 cycles here. There is the cycle of creating a model, training and evaluating it, and then changing the model in order to improve it, because typically I go through many experiments in order to get to a stage where I can actually get to a model that I'm sufficiently satisfied with. But also there is a cycle between deployments, generating data, which is then used to create new models, new training and evaluation, and new deployment. Also, there is a big loop where there is constant redeployment of machine learning models in the real world, in the system. And if we look at where all the attention goes, the attention is predominantly on creating models and training and evaluating. And to be honest, I had to smile a little bit when we had the keynote from the gentleman from NVIDIA yesterday, because one of the things that he mentioned, and not all of you may have heard it, but one of the things that he mentioned was, we don't need more algorithms. I'm not sure if you heard that. Yeah, but I thought that was a really interesting statement. But the interesting thing is everyone is concerned with new algorithms and new ways of training and evaluating God knows what else. But if you look at where the real effort goes, in all the companies that we work with around machine learning and deep learning, the effort goes into getting the data sets in place and in getting the deployment in place. That's the hard part. This part in the middle is actually the easy part. That's not so difficult. We know how to create the models. We know how to train and evaluate. There are good solutions out there to do this stuff. It is, how do I get a data set in place that I can actually rely on, and how do I get the deployment in my products in place in a way that I can trust, that I can give this product to customers and without having them call me in the middle of the night. So those are the things that I wanted to spend a little bit of time on. And then what I will briefly do, and I will only have a few seconds of this because I'm already, I only have 10 minutes left. 3 studies. We did a first study a few years ago with my friends from Peltarion. Peltarion is a company in Stockholm, actually funded by the Wallenberg family, among others. That is building a platform for deep learning systems. If you don't know about them, I would really recommend that you take a look at their platform. With some of the people there, one of the founders and 2 of the people working there, Anders and Björn Brine, we looked at 7 projects that these people had been involved in around real estate validation, predicting oil and gas recovery, predicting user retention, weather forecasting, credit card fraud detection, poker bot identification, and media recommendations. And we classified and studied what are these software engineering challenges that we can find in these ways of working. And what we did was we categorized those challenges into 3 categories: development challenges, production challenges, and organizational challenges. And then we mapped them on a graph where we said lower business impact and high business impact, and then easier to solve to hard to solve. Now, one of the things that we often see is experiment management is actually quite tricky until you have unless you have good tooling available. Because I try out so many different experiments, I try out so many different models, and I train them and evaluate them, sometimes with different data sets, keeping track of which experiment generated which quality output with which data set, and what of these experiments can I then actually rely on and deploy in practice, is actually becoming very easily rather messy. Another one which we ran into, which you see up here, is the notion of effort estimation. Yeah, for all of you that work in industry or have worked in industry, imagine going to one of your key decision makers and saying, I want to do a machine learning or deep learning project. And the key decision maker says, okay, how long is it going to take? And your answer is, I don't know. What is the benefit that this project is going to give? I don't know. Yeah? How many people are you going to need? I don't know. How likely do you think that you will get the funding for this particular initiative? Zero, exactly. And the problem is that in many machine learning and deep learning projects, you don't know what the quality is or how good the model is going to be, how well it will perform in practice, until you actually try it out. But trying it out means that you have to go through the whole process of assembling the data sets, creating the models, actually training and evaluating them. So it's actually taking quite a bit of time. Another one is cultural differences. I'm not sure if any software engineers in the room have worked with data scientists, or any data scientists in the room have worked with software engineers, but these are two different beasts. Yeah, they think very, very differently. Data scientists don't care about scalability. They don't care about industrial deployment. They don't care about testing. They just care about the final numbers on the system that we're talking about. How accurate is this thing? Well, how far can I push the errors down? Another one is glue code and supporting systems. So there are lots of problems, and if you're interested in it, or challenges that need to be worked on, but we have things from experiment management to limited transparency. How do we actually, the thing works, but why in heaven's name does it work? Troubleshooting, things don't work as expected, but you have very large libraries built often by data scientists, meaning that it's not the most well-engineered solutions very often. Sorry about that. Yeah, so troubleshooting is very hard. Resource limitations, we still, for all the work on GPUs and everything else, we run into a situation where it actually becomes very hard to run the things we want to run. I mean, if you look at more advanced deep learning models, you can talk about 100 or even hundreds of layers in a deep learning model. If you talk about industrial deployments, those things are not easy to train if you also have very large data sets available. Testing of data. How do I know that my data set is representative? Is also a very difficult challenge. It's not just testing software, it's also testing my data sets. Or production challenges. Yeah, dependency management. GPUs are changing constantly, and what you very often do is you manually optimize the code that you are deploying for the specific GPU architecture in order to get maximum performance. Monitoring or logging. Unintended feedback loops is also a very interesting one. If you are Spotify and you recommend certain songs based on your algorithms, the moment you recommend that song, it's going to be listened to by more people, and because it's listened to by more people, it becomes more likely to be recommended the next time around, and then you very easily get into these positive feedback cycles where you actually get feedback loops that are not intended. Effort estimation, I already talked about, privacy and data safety, and then of course cultural differences. We did a second study with a few other companies in the automotive space, a few in the web space, and in the telecom space, where we looked at numbers of interviews from a number of people. And here we basically categorized the challenges along the experimental prototyping, non-critical deployment, critical deployment, and then cascading deployment that I already talked about. I'm starting to wrap up because we're running out of time. And then we looked at the 4 activities: assemble the data set, create the model, train and evaluate, and deploy. And we see very typical problems. In non-critical deployment, what we see is that many companies run into a training serving skew. So what that means is that the data that I've used for training my model and the data that the system gets in live operation are actually so different from each other that the performance of the model is actually not going well. If we look to critical deployment and we look at the training and evaluation, difficulties in reproducing models and in debugging deep learning models is proving to be very difficult as well. If we look at cascading deployment, then we have the challenge of entanglements, which makes it really hard to isolate improvements. So if you look at companies like Microsoft, where one of our former PhD students is now working, they actually deploy deep learning and machine learning models in an A/B testing context where the old model and the new model are operating in parallel. Both get served a certain amount of the traffic, and then we measure if the new model that performs better in training also performs better in operations, which is not necessarily the case. And then the third study is specifically around data management challenges, where we looked again at product recommendations, weather prediction for wind power, house price prediction, looking into automated classification of skin lesions in skin cancer or potential skin cancer, credit card fraud, and predicting quality of paper output or paper boards in manufacturing. And we looked specifically at what are the data management challenges. And what we see is that we look at the following phases in data management: data collection, exploration, pre-processing, preparation, testing, deployment, and then post-deployment. And there are a number of challenges that are concerned with each of the phases in the data, in the management of the data. So this is just the first box of the 4 boxes that I showed you earlier. We did this for a number of case study companies, and we see that things of a lack of metadata. That is one of those typical challenges. Most companies don't have a unified data warehouse, which means that different teams, different functions have collected data for their own purposes. And then you take data from one of the teams, and it has a certain name associated with certain columns in your data set, and you think you know what it means. Yeah, and you go and use it based on your understanding of what that particular data is supposed to mean. But in practice, it doesn't mean that. It means something completely different. It's just that these people have used a different name for this. Statistical understanding, I must admit that I didn't do too well on my statistics scores in university. And to be honest, I'm far from the only one. Many other people have some difficulties with understanding statistics. And you know the saying, there's always lies, big lies, and statistics, right? I mean, that's the motto. You can explain everything by using incorrect statistical understanding. Data dependency tooling, expensive testing, overfitting is one of those other things that we see a lot. So there are lots of challenges related to this as well. Conclusion, and I'm leaving 3 minutes for questions, sir, which is what you asked me to do. So I think I'm delivering, actually. Don't you think so? Yeah, good. So conclusion, we live, and I really believed it, I believe we live in the most exciting time in the history of mankind. Really. If you look at the amount of progress that we've made over even the last 50 years, if you look at life expectancy, poverty, child death, war deaths, all kinds of things, we have never lived in a better time. And the progress that we are experiencing as society is only accelerating. I understand the importance of ethics and the understanding of what this means for society and all these other good things, but we should not forget that we live in the best time that mankind has ever experienced. And thanks to digitalization as a technology, the pace of change is only accelerating. The improvement that we're going to see as a society is only accelerating. And this is thanks to digitalization, which is software, data, and AI. Yeah? So I really want to reinforce them. I'm a hardcore modernist. I know that everyone talks about it, the world is going to hell in a handbasket. The data doesn't back it up. And if you want to have any evidence on this, read The Rational Optimist, which is a great book, which basically does away with all kinds of the world is going to hell stories that we're experiencing. However, if we want AI, machine learning, and deep learning to actually bring that impact to society that we're all looking for, then we have to understand that deploying this in production quality context, industrialized deployments, is a major engineering challenge. And in order to meet that challenge, we need to balance the work, the research that takes place on AI, with sufficient work on software engineering on AI, because otherwise we'll end up with an ivory tower filled with great ideas that will never see the light of day in society, because we don't have the engineering solutions to actually deploy what we're actually doing. And with that, my friends, thank you very much for your attention. I appreciate it.
Thank you very much. Any comments?
Sir.
So, this is Saif Haridi from KTH and 6.
Yes, earlier today.
I think your talk is extremely good.
Thank you. But here comes the but.
Here comes. No, I just want to. But just, I mean, the issues that you raise are actually very realized if you go outside to industry and even researchers So this year, they start a new conference called Systems for ML.
Yeah.
And Systems for ML is really trying to address many of the issues that you're talking about. The first conference was in Stanford 2 weeks ago. And basically addressing these issues.
Yeah.
How to really take the whole pipeline of machine learning and to really to do applications, because the companies are really failing with using AI technology today. Second thing, just a comment, experiment management. So there is now a community around a new open source called MLflow. MLflow is really great. Many companies and universities are there to really build an open source system for experiment management. It's called MLflow.
Right. Yeah.
Okay, and thank you for your talk.
No, I mean, I think you're making a great point. I'm not claiming that I'm the only one who talks about software engineering for AI. I think that that's important to realize. What I'm looking at is, if I look at all the investments, I mean, for those of you that were here yesterday, I mean, 4 billion out of the Wallenberg family. If we look at all kinds of different initiatives around the world, the amount of money that pours into AI is just amazing. And I'm wondering, what is the relative focus between the AI research around the algorithms and everything else versus the engineering practices? And I fully agree with you that the awareness is starting, because the Jonas that I started with, that's not one Jonas. There are dozens and dozens of Jonases out there that I'm aware of where AI and machine learning initiatives actually failed because of the engineering challenges. So it's becoming aware, but we also need to really invest more into it, I think. I think it requires more attention.
Well, no, safe. That's
partner conference in need.
Okay.
yeah. We'll take one more
Thank you.
question.
You're gonna. I think you're. And then
I think your image with the doghouse and the skyscraper is just misleading, because the AI has been sort of characterized by big scale, solving, I mean, millions of images and so forth. I mean, I don't know. Is it software engineering you're referring to, or is it AI research? I mean, what's your comment on that?
Yeah, what's my comment on that? Yeah, I got already some feedback on that. Maybe I should have been a little careful with the doghouse versus the skyscraper. Here's the thing. One of the reasons that machine learning and deep learning has done so well is because the amount of data that is available has basically gone through the roof. But I see a lot of research being concerned with how do we still squeeze another promille of improvement in algorithms out of the models that we are building using larger data sets and larger models, basically. What I do not see researchers spend as much energy and time on, and that's basically the pitch that I was trying to make this morning, is in how do we then actually go and take those solutions and those models and those technologies that we have now developed and actually prepare them and make them ready for industrial production quality deployment. And I think that that's where I see a major gap, and I see that the AI community at large, at least from my perspective, is not recognizing that enough, even though the first transition is starting to happen in that space. So that's where I'm coming from.
Thanks. Let's leave it here and continue with the next. Oh, and thanks, speaker again.
Oh, well, thank you, sir. Thanks.